Hello all, welcome to my channel. This video we will talk about system design. Basically, we will be discussing few trade-off theorems. So let's get started. So in a distributed system, there are different properties which we have to balance. We can't have all the properties in one system, and these properties are like consistency, availability, latency, partition tolerance, query pattern, scale. So these are properties of distributed system, and we have to choose for certain systems certain properties and sacrifice the other properties, and that's what we call a trade-off. There are many theorems which have been created to handle these trade-offs that we might be making, and they guide us in making that architectural decision that what trade-off we should be doing. So the first theorem that comes is cap. Cap states that in presence of a network partition, a distributed system will choose between consistency and availability. So given a partition tolerance, means network partition, we will have to either choose availability or consistency. We can't choose both. So this picture denotes systems which have uh, partition tolerance. For example, let's say this circle is for partition tolerance. So either we can choose consistency. So that system becomes CP, which is we have systems like MongoDB, HBase, and Redis. So they prefer consistency over availability. So that means that the system will go down to remain consistent. In case we choose availability, then we are losing on consistency and saying that, okay, in case the partition tolerance is there, system will still be available, but it might give wrong or incorrect or stale results. And let's say if we don't have a partition, don't have a partition, a network partition, that means we are having a single node systems, for example, RDMS or MySQL. So that those can choose consistency and availability because there is no partition tolerance. They can be consistent as well as available. But again, ability, this partition tolerance doesn't come into picture for those systems. So this is based on this CAP theorem. Uh, we say that which aspect or which property of the system we will be taking to make systems work, and which properties we will lose. And it is this theorem is very useful in understanding the failure mode behavior, like which mode of failure that we are choosing. And consistency, what does it mean is that all nodes in the system see the same data at the same time. They don't have in out of sync uh, data. Availability means every request that is received must get a response. Although it means that uh, we might be giving a older or a wrong result, but what we are guaranteeing is that every request will have a response. And partition tolerance is system continues to operate in case we have network failures. So in case we have a node, three node system, let's say there is a network partition that happens and only two nodes are there. So if a request comes to the system, if we are opting for consistency, either of the two nodes which are there will return the response, but they might respond with a wrong result. If we are choosing for consistency, then both of those nodes should have data in sync, and that then we respond with the right result. So that is how consistency and this cap theorem works. An example, as I said, CP is Mongo and HBase, AP is Cassandra and DynamoDB. So this was the first trade-off theorem. Then this trade-off theorem was extended further by a theorem called PACE-LC or PALAC, we can say. What it says is, in case there is a partition, we will choose availability or consistency, which is nothing but a cap theorem. But if there is no partition, then also we choose between latency and consistency. Okay, so this latency part is added as an extra layer. So this what it means is this will give us an option to treat the system in terms of latency as well. This under a good network condition, how much latency we want, or how fast we want our system to be, and to make the system faster, are we going to lose some consistency? So that's what this theorem says. For example, DynamoDB, which uh, is available under partition. So it chooses the PA part. In case of partition tolerance, it chooses for availability, and then it prefers latency under normal conditions. So it prefers to have a faster response rather than giving a consistent response. So it gives consistent response, like it follows eventual consistency. So over time we will get the right results, but it prefers latency in that case. And in case of Spanner, which is Google's product, it chooses consistency in case of a network partition is there, else it chooses uh, so basically it chooses always chooses consistency over uh, over latency. So it will provide a higher latency, but it will always be consistent. So this theorem is very interesting, and we should be knowing about this in cloud systems for sure. Then there is a pi theorem, which says that in case of a cloud or any system which is giving us scale and efficiency and pattern flexibility, we can only choose two. So what does this mean is that in case we want to create a system which is infinitely scalable, so either we can make the system infinitely scalable with an efficiency, or we can make a system infinitely scalable with a pattern flexibility. Pattern flexibility is how how many ad hoc queries we can support. So if you see Athena or Redshift of AWS follows infinite scale and pattern flexibility. So we can query because it follows, for example, we can write our own query at the time when we issue the queries. So that's and then Redshift is another example which gives us infinite scale and pattern flexibility. But when it comes to efficiency and pattern flexibility, so RDS and OpenSearch are examples of that. So what in this case, what we are looking at is we want an efficient system which works well with ad hoc queries. So this is that part. Then we have infinite scale and efficiency. We are losing on the pattern flexibility. What does this mean is when we are choosing what DynamoDB chooses is that it remains scalable, highly scalable, and it chooses efficiency. It does not give us pattern flexibility. So we have to know when we do a table design, we have to know the query pattern beforehand if we want to make it highly efficient and infinite scale. So we can't use the same table for ad hoc queries and get the efficiency. So this is a pi theorem. This was coined by some developer at Amazon, and it's makes sense because there are systems which follow this approach. For example, uh, uh, Kafka is a system which chooses a pattern flexibility with infinite scale over efficiency because it follows at least once. It can do. That's what it says, that it will deliver. It will sacrifice exactness, which is the efficiency part. So this means the terms are defined in like pattern flexibility means that there the ad hoc queries can be done, or it will only allow a fixed access pattern. Then infinite scale supports high throughput and scale, and efficiency is a strong correctness. So what Kafka does it says that okay, I will choose for a pattern flexibility, like you can query whatever however you want, but I will and it will give an infinite scale, but it will not provide you exactness, which is the efficiency part. Because it may deliver things more than once. So this is not exactly once; it is at least once. For example, spanner that we discussed in here, it also follows this PE approach, which means that it does not give pattern flexibility, but it gives good correctness because it chooses consistency and it chooses for efficiency. It does not rely on the pattern flexibility. So we can do, generally we have to know the query pattern beforehand for spanner. Then we have another trade-off theorem which says, which is FLP impossibility. This is for consensus in asynchronous systems. What it says it that in an asynchronous system, it is impossible to guarantee consensus if there is a node failure. So what it says is agreement, termination, and validity. These are three different uh, areas, and in which we can only choose two. We can't choose all three. So for example, we can't have a system which is fault tolerance and is also always have a state, a terminating state, and can support partition tolerance. So can support loss of a node. So based on these, we have different systems. Let's first discuss the attributes which are there. So termination means all nodes will eventually decide which value to be considered as the right value. Agreement is that all nodes that decide uh, on the same value. If all nodes have the same initial input, the value should be the only possible decision value. And fault tolerance means all nodes require that a protocol must also be effective in case of node failures. So if we see here a few examples is uh, in a we can't guarantee a consensus if we have in case we have fault tolerant and always a terminating system is there. This is critical for designing leader election algorithms like quorum, gossip, uh, and other systems. So for example, if we decide on to choose between liveness and fault tolerance, then we will go ahead with two-phase commit. If we decide between liveness and partition tolerance, we go ahead with gossip protocol. If we want to choose partition tolerance and fault tolerance, we go ahead with Paxos. So these are some consensus algorithms and which one to choose based on the attributes of the system. Then we have a yielding triangle, which says that this is a four-way trade-off where we say that in case we will have to take considerance, we can only take three out of these systems. Like we can either choose consistency, latency, and availability, or we can choose latency, availability, and throughput, or we can choose consistency, availability, and throughput. We can't take all those four in one. So here we have this table which says consistency, latency, and availability. And if we choose this, so we want a system to be highly consistent with a low latency and highly available. So we choose Redis or Zookeeper. So we uh, what we are giving up is the throughput. So we are saying that okay, we will not be able to serve requests at a very high rate because we want the system to be consistent, but uh, we are giving responses in very low time and the system is highly available. Then we have CLT systems, which is OLTP RDBMS, where we are losing on availability. So we can't tolerate any partition failure or node failure. Then we have CAT systems, which are here we are compromising on the latency to give a higher throughput and consistent system. So we are see, because these systems are cross region, so the region latency will be there. Then we have LAT systems, which does not have a consistency in them, but they become what they uh, uh, lose is they lose on the consistency part, because they say that their systems will become eventually consistent rather than being consistent from the beginning. So yeah, this is a few uh, toleration things that we have, which we say as a yielding triangle theorem. This picture is for this picture says that which consensus algorithm we are talking will have what. So for example, if we are using gossip protocol, the consistency will be moderate. In case of two-phase commit and quorum, the consistency will be high. Transactions is fully supported in gossip uh, uh, and partially in these systems. Transactions will be always full support in 2PC and quorum. For 2PC and quorum, the latency will be high because it has to achieve that quorum before it responds with the right value. In case of gossip, the latency is low because it does not rely on multiple nodes to agree on something. It simply says that we are discussing and we just updated each other about our values and we respond back with that. So in case of gossip, we can have some data loss, but because in quorum or two-phase commits, we don't doesn't have a chance of loss of data. And failover, gossip, two-phase commit, and quorums do support read-write failures, while others only support read-only. And there are a few other trade-off theorems. One is on acid and base. So this is not an trade-off per se. This is just about two different systems. One says acid systems have these properties, like they are atomic, their transactions are isolated, they give a consistent view, and their system is durable. And the base systems are there, which says that they want to be always available. They lose uh, some state for eventual consistency. So uh, this builds base for uh, NoSQL databases as well, which are highly available, but they follow eventual consistency model and a soft state. So to summarize things that we have discussed in here is the pattern and so we have discussed about cap theorem, Bayes theorem, and cap theorem, pi theorem, and Bayes systems. So the lambda architecture is an example of those. And for PSLC or pi, we have event sourcing and CQRS. That can be an example of that. Cloud native spanner like DBs follow this flip and faculty. Database systems follow Pi, and Apache Kafka and Pulsar follow Pi or AP systems in favor of latency and scale. And this is the summary that CAP theorem says CA and consistency and ability trade-off under a partition, and this is foundation of the NoSQL systems. PSLC adds latency consideration when there is no partition at all. So it will choose between latency and consistency in case there is no network partition. Pi is something which says uh, what we want, whether we want scale or we want correctness in the stream systems. So streaming architecture to follow that. FLP is impossibility of the consensus. So how we design raft or Paxos algorithms. This is based on these trade-offs. Base versus listed is something which is about what type of DB we should be choosing for a system. So this was it for this video. We will come with another video on system design series. So keep watching this space. Have a nice day.